That was an introduction to the Bellman Ford algorithm. Now we look at how it actually works. So we are now going to run the Bellman Ford algorithm on this graph. Note that it has negative weighted edges. We first initialize the distance table, just like we always do. So there is an entry for every vertex in the distance table, and the initial distance of all the vertices is infinite. To start running the Bellman Ford algorithm, we can choose any vertex at random. Since this algorithm covers all the edges in the graph v minus 1 times, we can essentially start with any vertex and we'll get the exact same result. So, in order to find the shortest path between any two vertices, you can start the calculation of the shortest path and filling the distance table from any vertex. Remember that you just choose a vertex at random. For the first iteration, we start with vertex A at random. We start with vertex A and explore all its neighbors. The first neighbor that we explore is vertex B. The distance of B is the distance of A plus the weight of edge A, comma B. And as you can see, the distance of B will be 2 to start off with. The distance of A is 0 because that's the source. Now, let's explore the edges of B. The distance of D is the distance of B plus the weight of edge B, comma D to get 5. Remember, the important thing here is not exploring the vertices, but exploring the edges. Make sure you cover every edge. That's the important point here. Let's now look at the edge from B to E. It has a negative weight. So the distance of E is the distance of B, that is 2, minus 2, that is the negative weight of edge B to E, which means the distance of vertex E is 0. Explore the edge now from E to D, which has an edge weight of 1. D is already present in our distance table with a distance of 5. However, the new distance is smaller than 5. So we basically update the distance table with the new distance, which is equal to the distance of E plus the weight of the edge E to D equal to 1. The next edge we'll explore is the edge from A to C. It's still unexplored, and the distance to C will be 1. The distance from A is 0 and the edge weight is 1. What are the unexplored edges? The one from C to E. So the distance to E can be calculated as the distance of C plus the weight of the edge C, comma E, which is 1 plus 2 equal to 3. However, E already has a distance of 0 associated with it. 3 is greater than 0, so we ignore 3 and do not update the distance of E. And finally, we explore the last edge in the first iteration, that from C to B. The distance of B, if you sum it up through C, is 1 minus 5, which is equal to minus 4. Minus 4 is smaller than the distance that was existed at B, equal to 2 earlier. So we replace 2 with minus 4. After the first iteration, the distance table will look something like this. This is the distance table after the first iteration in our Bellman Ford algorithm. There are entries for every vertex, and the distance to that vertex is specified in the distance table as well. Notice something about the distance to every vertex. You'll see that the distance to vertices B and C are accurate. Distances which are at a one edge distance from the source that we've chosen are accurate. the remaining distances are not accurate and we need further iterations to get accurate distances for the remaining vertices. So once more, we go to the next iteration and apply and calculate new distances to input into the distance table. Once again, we start from A to B. The distance is 2. And since 2 is bigger than the distance already available to B, we simply ignore it. So we ignore 2 and leave the distance of B as -4. Let's explore the next edge. The next edge goes from B to the vertex D. The distance to B is now -4. We have a newly updated distance to B. So the distance to D will be -4 plus 3, which is equal to -1. So that's the new distance of the vertex D. Let's go on and explore the next edge between B and E. Here, once again, we have a new distance to E. B is -4 and the edge between B and E is -2, which gives us a new distance of -6. The next edge that we explore is between E and D. -6 plus 1 gives us a new distance for D yet again. So -1 we can get rid of, and the new distance to D is -6 plus 1 equal to -5. Other edges to explore between A and C. We have the right distance, so we can move on. Then between C and E. The distance now from A to C to E is 3, but we already have a better distance to E, that is -6. So we can ignore 3 since 3 is greater than -6. We finally explore the last edge between C and B. Once again, this distance is -4. We already have updated B with the correct value -4. So we are done. We've explored all the edges once more in the second iteration. After exploring all the distances, all the edges, we update the distance table with the new values. So there it is. Here we have the distance table after the second iteration of relaxing all the edges in this graph. If you notice now, the distance to every vertex is accurate. After this iteration, all distances are accurate. It so happened that we got accurate distances for all vertices from source A with just 2 iterations. The graph is set up such that this was possible. However, for the Bellman-Ford algorithm to work on any graph, we have to guarantee that we find the shortest path in any graph, we need v minus 1 iterations. We'd mentioned this earlier, and now we'll logically see why v minus 1 iterations are needed. Now, the longest possible path in a graph of v vertices has v minus 1 edges. This is when the graph is one long line of vertices. You have an edge connecting every vertex. So for v vertices, we have v minus 1 edges. This is the longest possible path in a graph. After one iteration, all vertices which are one edge away from the source vertex that we've chosen are accurate. This makes sense because we have to exhaustively explore all edges to get the correct accurate distance for every vertex. In one iteration, we would have explored thoroughly all edges which are all vertices which are one distance away from the source edge, and the distance for those adjacent vertices which are one edge away will be accurate. After two iterations, all vertices which are two edges away from the source vertex are accurate. That's because we would have successfully explored all paths which are two edges away from the source. So all paths which lead to vertices two edges away would have been explored. We will have accurate information, distance information for those vertices. And after three iterations, all vertices which are at a distance of three edges away from the source will have accurate distance information associated with it. So at every iteration, we have accurate distance information for vertices that many number of edges away from the source. Which means if we do v minus 1 iterations, we can guarantee that the vertex which is furthest away from the source will have its distance accurately calculated. Because this guarantee only exists at the v minus 1th iteration, we need at least v minus 1 iterations for the Bellman-Ford algorithm to give accurate results.